Dr. S. Nagan. He is an associate professor in civil engineering at Tyagarajar College of Engineering, Madurai. He pursued his undergraduate and postgraduate studies from Tyagarajar College of Engineering and completed his PhD at the Madurai Kamarajar University. He has more than 20 years of teaching and research experience. He has worked in many prestigious institutions including PSNA, College of Engineering and Technology, Dindigul. He has published more than 25 research papers and 5 books under his name. Apart from all this, he is a life member at the International Society for Environmental Protection and also at the Indian Society for Technical Education. To add to all of this, he is won the Best Staff Advisor at the ISTE Students Chapter.
Welcome to the UGC lecture series for Bachelor of Architecture. In this lecture, we will be focusing deflection of beams, mainly simply supported beams subjected to several point loads and also a simply supported beam subjected to uniformly distributed load. We will use the mechanism method which we studied, and then we will also use the double integration method in case of simply supported beam with uniformly distributed load. In continuation to the earlier example, say we have been discussing a simply supported beam with non-central load, say we had 1 meters here and we had 1.8 meters here. So, span is 2.8 meters and we have developed the equations of slope and deflection, and we need to obtain the constants of integration using the boundary condition. So, the boundary conditions will be, say at x equal to 0, deflection will be 0, and at B where x equal to 2.8 meters deflection will be 0. So, when x equal to 0, y equal to 0, and when x equal to 2.8 meter, y equal to 0. Using the boundary conditions in the deflection equation up to dotted line, that is the first boundary condition has to be used for portion AC alone. Then for portion CB we can use the entire equation. So, substituting that we will get C2 equal to 0, and then substituting the boundary condition 2 in equation 3 we will get C1 equal to 29.57. So, after obtaining C1 and C2 we can have the general equation for slope as this and general equation for deflection as this. We have the general equation for deflection as minus 38.57 x cube by 6 plus 29.57 plus 60 into x minus 1 whole cube by 6. So, if we need deflection at any point in portion AC, we can use the general equation for deflection up to the dotted line, and if we are interested in obtaining deflection in any point in portion CB, we can use the entire equation neglecting the dotted line. And say if we are interested in finding the maximum deflection, say the simply supported beam subjected to non-central point load. So, it will deflect in this fashion, and it need not be necessarily that the maximum deflection occur under the loaded point. So, it may be anywhere here or it may be here to the left of the load or to the right of the load. So, we need to exactly locate the point of maximum deflection. So, we can locate the point of maximum deflection by equating the slope to 0. So, here comes the guessing of the probable point of maximum deflection. First, we need to assume that maximum deflection occurs in portion CB or in portion AC. Accordingly, we need to equate the slope equation to 0. So, if we assume that the maximum deflection occurs anywhere in between portion AC, then we need to equate the slope equation up to dotted line to 0. But if we assume the slope is 0 or the deflection is maximum in portion BC, then we can use the entire slope equation and equate to 0. So, here let us assume that deflection is maximum in portion BC and we are equating the entire slope equation to 0, thereby we get x equal to 1.29 meter. We will be resulting in with some quadratic type of equations while involving the equation of or equating the slope to 0. So, while getting quadratic values, you should or we should take the correct value. Say we have the span 2.8 meters. So, we have got x equal to 4.29 meters or 1.29 meters. So, 4.29 will be an observed value and hence 1.29 meter will be the correct value, because we have span only 2.8 meters. So, this is the problem. We have the load here, this is 1 meter and this is 1.8 meter, and it is clearly we have got the value of 1.29, which will be lying somewhere here after portion. Say this is portion A B C. So, the assumption which we have made that the maximum deflection occurs in portion B C is correct. In case if we get a value lesser than 1, then we need to redo the calculation by equating the slope up to portion A C, that is up to the dotted line to 0, and then we should revise the value of x, and then by substituting the value of this x in the deflection equation we will be getting the maximum deflection. So, deflection will be maximum at 1.29 meter from A, hence substituting this value in the deflection equation we get maximum deflection of 6.15 mm. If we find deflection under the load point, say if you are interested in finding deflection under the load point, then we need to put x equal to 1 meter in the general equation for deflection up to the dotted line, and we will be getting a value which will be definitely lesser than the value of 6.15 meter. You can make a try and you can find the value of deflection exactly under the load point. We have found the maximum deflection. Next, we will proceed to several point loads or 2 point loads in this case. So, we have a simply supported beam of span 14 meters and subjected to 2 point loads of 12 kilonewton at 3 meters and 8 kilonewton at 9.5 meters from the left end. We will have to compute the deflection under the load points and also the maximum deflection. The Young's modulus is given as 200 GPa and I value is 160 into 10 power 6 millimeter power 4. So, first let us find the reaction components R A and R B. So, here we need to make use of the static equations of equilibrium to obtain the reactions R A and R B. We have sigma V equal to 0. So, using that you will get R A plus R B minus 12 minus 8 equal to 0. Therefore, R A plus R B equal to 20 kilonewton, and then using sigma m equal to 0, using sign convention clockwise positive and taking moments about A, you will be getting 12 into 3, because the 12 kilonewton produces a moment of 12 into 3 about A, and 8 kilonewton load produces a moment of 8 into 9.5 about A, and R B produces a moment of R B into 14 about A, and these two loads, applied loads, produce a clockwise moment and the reaction component produces anti-clockwise moment. So, plus and minus we have taken like that. Then R A and R B equal to R A equal to 12 kilonewton and R B equal to 8 kilonewton. After obtaining the values of reactions, then we can start writing the bending moment equations in different portions. Say if we want to develop the equation for portion A C, bending moment at x x will be equal to this left reaction we have 12 kilonewton, 12 multiplied by x will be the bending moment for portion A C, and it should be clear that it produces a clockwise moment, and being to the left side of the section, left clockwise being positive, it is plus 12 x. Then we will move the section to C D, So, at this point we have this 12 kilonewton reaction and the applied load of 12 kilonewton load. So, the reaction produces a moment of 12 into x, and it being clockwise, left clockwise positive, and the applied load of 12 kilonewton produces anti-clockwise moment about the section, and it produces a moment value equal to 12 into x minus 3. So, one is plus and minus. So, and the other is minus. We need to use the sign convention which we have been practicing for the all the cases of our problems, and then we can arrive the bending moment equation for portion D B. So, for portion D B we have this 12 kilonewton upward reaction and downward loads 12 kilonewton and 8 kilonewton. So, the reaction will produce a moment of 12 into x, then the applied load 12 will produce a moment of 12 into x minus 3, and 8 kilonewton will produce a moment of 8 into x minus 9.5. So, the reaction produces clockwise moment while the applied loads produce anti-clockwise moment. So, plus and minus are assigned accordingly. If we notice the three equations, say the first equation is 12 x, and second equation is 12 x minus 12 into x minus 3, and the third equation is 12 x minus 12 into x minus 3 minus 8 into x minus 9.5. So, if we take or compare the equation for the portions, the 12x being common for the all the 3 portions and minus 12 into x minus 3 is common for portion C D and D B. So, we can write the equation like this: E I d square by d x squared equal to minus m x x. So, minus open up bracket 12 x for the first portion, separate by a dotted line, and then additional term which we have for the next portion is minus 12 into x minus 3, and then put a dotted line. Additional equation or additional term for the portion D B is minus 8 into x minus 9.5. So, we need to write in this fashion, which we have been practicing for the earlier examples also. The example of a simply supported beam with central point load, and also we have seen a simply supported beam with non-central load. In both the case, we have been practicing this method of writing the bending moment equations portion by partitioning technique like this, as suggested by Macalise. So, we have E I d square by d x squared equal to minus 12 x separated by a partition plus 12 into x minus 3, then dotted line plus 8 into x minus 9.5. The other procedures will be routine. We need to integrate twice the equations, and then we will be getting 2 constants of integration. Substituting the boundary conditions, we will be getting the values of constants of integration, and then substituting back in the equation for deflection and slope, we will get slope general equation for slope and deflection, with which we can calculate the slope and deflection at any required point. So, we have integrating with respect to x, we have E I dy by dx equal to minus 12 x squared by 2 plus C 1 plus 12 into x minus 3 whole squared by 2 plus 8 into x minus 9.5 whole squared by 2. So, if we notice in portion AC and CD, we will be having the term x minus 3 and x minus 9.5, that they should be considered as a single term, and integrated we get x squared by 2. We should not separate, that is to be taken or borne in mind. Then integrating this equation again with respect to x, we have minus 12 x cube by 6 plus C 1 x plus C 2, and the next term will be x minus 2 whole square by 2 now will become x minus 2 whole cube by 6, and x minus 9.5 whole square by 2 will now become x minus 9.5 whole cube by 6. And then the boundary conditions, say we have simply supported beam, we have 2 point loads, say the beam will deflect in this fashion, it will be deflection will be 0 at the left end and at the right end. That has been mentioned or taken as the boundary conditions, say when x equal to 0, y equal to 0, and when x equal to 14 meters, y equal to 0. So, using these boundary conditions in the equations, we can get the constants of integration. So, care should be taken to use the entire equation or the equation up to dotted line, that is more important to obtain the constants of integration. So, the first boundary condition will be x equal to 0, y equal to 0. So, when x equal to 0, y equal to 0 lies in the region AC, and hence the equation first equation need to be used up to the first dotted line alone. If that, we will get C 2 equal to 0, and then if we use x equal to 14 meters, y equal to 0, the entire equation can be made use of, because x equal to 14 meter covers the entire length. So, entire equation can be made use of, thereby we get the value of constant C 1 as 193.18. Now, we will be having the general equation for slope as E I dy by dx equal to minus 6 x squared plus 193.18, that is the constant first C 1 plus 6 into x minus 3 whole squared plus 14 into x minus 9.5 whole squared. This will be the general equation for slope, and general equation for deflection will be E I y equal to minus 2 x cube plus 193.18 x plus 2 into x minus 3 whole cube plus 1.33 into x minus 9.5 whole cube. So, equations A and B always form or be the general equation for slope and deflection respectively. Now, we are interested in obtaining the slope at supports and deflection under the load points. So, to obtain slope at the supports, say if I want slope at support A, I need to substitute x equal to 0 in the general equation for slope up to the first dotted line, and then if I want slope at B, we need to substitute x equal to 14 meters in the equation A. The entire equation can be made use of. Similarly, if I am interested in finding deflection under the load points, say if I am interested in deflection under first load, so I need to put x equal to this value, whatever value we have here in the problem. Say we have 3 meters. So, this is 3 meters and this is 6.5 meters. So, we need to substitute x equal to 3 meters if I am interested in finding deflection at C, and I will have to make the general equation for deflection up to the first dotted line, and if we want deflection at D, I will have to make use of the general equation for deflection up to second dotted line. Up to second dotted line I need to substitute. So, that indicates the portions or where our point of interest lies. So, to find deflection at C, we have put x equal to 3 meters in the general equation for deflection up to the first dotted line. E value is known, I value is given. So, we can calculate EI value. EI value will be getting in Newton millimeter squared, and since the load applied is in kilonewton and the distances are in meters, it is customary to have the value of EI in kilonewton meter squared. So, we have got 32 into 10 power 12 Newton mm squared as EI value, and if you convert into kilonewton meter squared, that has to be divided by 10 power 9 and it will be 32 and 10 power 3 kilonewton meter squared. When substituted in the deflection equation, we will get deflection in meters, and it is customary to explain or express always the deflection in mm. So, we get 16.42 mm is the deflection at point C, and when you want deflection at D, I need to put x equal to 9.5 meter in the general equation for deflection up to the second dotted line. So, if we put, we will get y d as 20.93 mm. So, we have got deflection under the load points. To obtain the maximum deflection, say this is the case, we need to assume where the maximum deflection lies, as we had assumed in the case of a simply supported beam with non central load, which is an example 2 which we have discussed earlier. So, this is portion A, portion B, C, D, or point A, B, point C and D. So, deflection will be like this, the beam will deflect like this. We have obtained deflection under load point C, we have obtained deflection at load point D, and somewhere in between there will be maximum deflection. So, from the deflection diagram we can easily judge the value of or the position or point where the deflection will be maximum, hence we can assume accordingly. So, let us assume that maximum deflection occurs in portion C D, and hence we can equate the slope equation up to second dotted line to 0 to get the point where deflection will be maximum. So, equating that up to second dotted line, you get x equal to 6.87 meters. We need to make a check whether this 6.87 meters is or meets up with the assumption which we had made. So, we have first portion is 3 meters and second portion is 6.5 meters. So, if our value x value lies well within 9.5 meters, then our assumption is correct, that is we have assumed the maximum deflection in between C and D. So, we got 6.87, substituting the value, you will get maximum deflection at 24.83. When this value compared to the deflection under the load points, it will be definitely greater, because we had deflection under D is 20.93 and deflection at C is 16.42, and this maximum deflection is definitely will be or should be greater than the values obtained under the load points. So, 24.83. So, that will confirm the correctness of the problem. And now, we will see the analysis of a simply supported beam with uniformly distributed load. So, in case of uniformly distributed load, say first we should find reaction as we have discussed. So, it is a uniformly distributed load spread over the entire length. So, naturally the reaction will be equal, and it will be equal to the total load divided by 2, it is W L by 2. So, here we do not have any portions. So, the mechanics method need not be required here, we have only one portion A B. So, the equation whatever we develop for the section x x will be applicable for the entire length A B. So, R A should be equal to R B, which is equal to W L by 2. Then M x x, bending moment at x x will be, say we have simply supported beam subjected to uniformly distributed load, we have section x x and this distance is x, this reaction is W L by 2, the load is W. So, bending moment at x x will be equal to W L by 2 into x, that is the moment produced by reaction W L by 2 about x x, and the moment produced by the UDL will be W into x will be the total load, and the distance will be x by 2 as mentioned here or as shown here, because the resultant will act at a distance of x by 2 from the left or from the section. So, W L by 2 into x minus W into x squared by 2 will be the mxx, and then E I d squared y by dx squared equal to minus mxx. So, minus W L x by 2 minus W x squared by 2, operating the minus sign inside, you will have minus W L x by 2 plus W x squared by 2, that is the equation 1. Integrating 1 with respect to x, we get E I dy by dx equal to minus W L x squared by 4 plus W x cube by 6 plus C 1. Then integrating 2 with respect to x, we get E I y equal to minus W L x cube by 12 plus W x power 4 by 24 plus C 1 x plus C 2. Again comes the problem of obtaining the constants of integration. So, when we are interested in constants of integration, we need to substitute the boundary conditions. So, again say we have simply supported beam. So, we should know the deflection pattern of the beam. So, the deflection will be 0 at the supports. So, at x equal to 0, deflection is 0, and at x equal to L, deflection is 0. So, you can use these two deflection boundary conditions in the deflection equation, and then we can obtain the constants of integration. So, using the boundary condition 1 in 3, we get C 2 equal to 0. Using boundary condition 2 in 3, we get 0 equal to minus W L power 4 by 12 plus W L power by 24 plus C 1 L. Thereby, we get C 1 equal to W L cube by 24. So, C 2 equal to 0 and C 1 equal to W L cube by 24. Now, we get the general equation for slope as E I dy by dx equal to minus W L x squared by 4 plus W x cube by 6 plus W L cube by 24, that is equation A, and the general equation for deflection is E I y equal to minus W L x cube by 12 plus W x power 4 by 24 plus W L cube by 24 into x, that is the general equation for deflection. Now, if we want slope at the supports, what we need to do? Similarly, if we want deflection or maximum deflection, what we need to do, that what we have to see. So, if I am interested in finding slope at A, so at point A x equal to 0. So, substituting x equal to 0 in the general equation for slope, we get E I dy by dx equal to W L cube by 24. Therefore, dy by dx equal to W L cube by 24 E I. So, slope at A will be W L cube by 24 E I. Then if we want slope at B, we need to put x equal to L in the equation, thereby you will get slope at the point B. And to find maximum deflection, because the simply supported beam subjected to UDL, uniformly distributed load, will be deflecting in this pattern, and we have found slope at A, we can find slope at B. So, somewhere the slope will be 0. So, we need to identify the point where slope is 0. So, where slope is 0, the bending moment will be or deflection will be maximum. So, equate the slope equation to 0. Here we get x equal to L by 2, and naturally in case of symmetrical loads, the deflection will be maximum at the center. In case of simply supported beam with UDL, or in case of simply supported beam with central point load, where maximum deflection will be occurring at the center, and that is evident from the analysis also. Now, substituting the value of x equal to L by 2 in the equation, deflection equation, will be getting the E I y max equal to minus W in L into L by 2 whole cube by 12 plus W into L by 2 power 4 by 24 this, and then we will be getting the deflection value as maximum deflection as 5 by 384 W L power 4 by E I. So, this is a standard loading case. Say we have studied simply supported beam with central point load. So, the slope at the supports will be W L squared by 16 E I. In either case, in both the slopes will be W L squared by 16 E I, and maximum deflection occurs at the center with the value being W L cube by 48 E I. Similarly, now we have derived a simply supported beam with uniformly distributed load over the entire span. The support slope will be W L cube by 24 E I, and the maximum deflection will be 5 by 384 W L power 4 by E I. So, this will be the maximum deflection. Why we are interested in maximum deflection is, while designing the beams, while designing a beam, any simply supported beam or cantilever beam or any beam, we will have to have a check over the deflection. So, after designing the beam, we need to find the maximum deflection using these relationships. So, we will be knowing the load, we will be having the span, we will be having the value of Young's modulus and moment of inertia can be computed using the cross section of the beam. So, we will be having the value of the deflection, and we have permissible limit for any deflection. So, in that case we need to check whether the deflection is safe. So, to conclude what we have studied so far, we have taken case of simply supported beams subjected to 2 point loads, and we have also seen a simply supported beam subjected to uniformly distributed load, and then we have arrived the maximum slope as well the maximum deflection. Slope will be maximum at the supports and deflection will be maximum at the center in case of central point load, and it may be anywhere in between the load and the support in case of non central load, and in case of uniformly distributed load it will be maximum at the center. Now, the questions will be, we will have some questions so that we can review what we have studied. So, obtain the slope at supports and deflection at C, D and the maximum deflection for the simply supported beam shown in figure. So, I have been given a simply supported beam problem, say subjected to 3 point loads. So, we have A, B, C, D, E. The loads are 10 kilonewton, 15 kilonewton, 8 kilonewton, and the distance is 1 meter, 1.5 meter, 1 meter and 1 meter. So, take E value as 200 GPa, I value as 10,000 centimeter power 4. Obtain the slope at the supports. The problem is obtain the slope at the supports and deflection at C, D and also the maximum deflection. So, herein we will involve what are the concepts which you have studied so far and we will be able to solve the problem. Thank you.